All right, class, welcome to section 2.2. We're going to continue our discussion of first derivative, critical points, relative mins and maximums, but we're going to apply those ideas to a little bit more complicated functions, which are the rational functions. So in 2.1, we graphed polynomial functions. Those are pretty easy. The graphs are nice, smooth curves. We already talked about that. No funny business is happening there. So we're going to do the same thing, but now with rational functions. So yeah, there's going to be a little bit of funny business, I must tell you. Okay, so I know you went through rational functions in college algebra, but I still wanted to give you a little bit of a review of what you've already learned. Okay, so I'm going to start right here first of all. A rational function is a function that can be written as a ratio between two polynomials. So remember the notation on polynomials that I gave you guys in the last section. It's the same thing, some number times an x to some power, some number times an x to a power less, and you go all the way down to maybe a number that's not multiplied to any x's whatsoever. Okay, so let me give you right here, write down what an example of a rational function might be. So let's say for example, 3x squared plus 8x minus 3 over x squared plus 2x minus 8. How about that? Okay. So that would be a rational function, right? It's got some polynomial divided by some polynomial. So what makes these functions behave funny is the fact that they're fractions. And as I mentioned a million times already this semester, which barely started, you cannot divide by 0. So there's going to be issues with zeros in the denominator. So I'm going to even write this down. Any rational functions you've learned about what we call parent functions, the parent function or the basic function of a rational function is f of x, or simply y, equals to 1 over x. Okay, so that's, if anything, the easiest looking fraction with x's on the bottom. A half is a fraction. It's far not as bad as 1 over x. Okay, and the graph of we call this also the reciprocal function. The graph of 1 over x looks exactly like that. So as you see, because x cannot equal to 0, and of course I know it came up in all the way out of 1.1 we discussed this kind of ratio. So because x can never be 0, the graph is not going to touch the y-axis or go through it. It's going to jump, but of course the closer and closer we get to tiny x values, the larger and larger the y values get, right? So this again should be familiar from chapter 1. Also, because you cannot divide by 0, 1 divided by any number that's not 0 will never equal to 0. So also the graph will never touch the x-axis. In other words, y itself will never equal to 0, right? And again, in a fraction, you can make a fraction, as I mentioned in the last section, you can make a fraction equal to 0 only if the top is 0. But this top is a 1, so it's never going to be 0. Okay. So in other words, the graphs of functions like this will very much behave this way. So they will have something called vertical and horizontal asymptotes. So for this graph right here, the two axes act as asymptotes. So right here, as it says, it's simply a line that the graph gets super close to, but it doesn't touch it. So here it is. This is a vertical, first of all, it's a vertical line. That's why it's called a vertical asymptote. But it's a line that the graph gets closer and closer to, but it doesn't touch it. The same thing the y-axis, right? The graph gets closer and closer to, and it doesn't touch it. By the way, you could have horizontal asymptote that the graph touches. So a vertical asymptote, the graph will never get close to it because, again, it comes from the fact, and I'll tell you in a minute, the fact that you're excluding those x values out of the domain. So x will never equal to 0. But just to mention it, I'll put it on the back since it's not really something that we're going to worry about. But you could have a graph that looks like this, which again, if you were to take calculus, you will be dealing with. So the y-axis is a horizontal asymptote. Why? Because the graph gets closer and closer and closer to, however, it does cross it a million times. Yes. So that's really what an asymptote is, right? So the graph gets closer and closer and closer to. Okay. All right. So what about this function right here? That's what we're going to be here to discuss. So the first thing we're going to be going over is stuff you've already learned, such as how do you find these vertical and horizontal asymptotes? And I am going to remind you right here, okay? How do you weave the graph through? Well, that's new. Now we're going to need derivatives. Those are going to be key into being able to graph these functions. As a matter of fact, you might even remember from your algebra classes, I know that was a big issue with my students when I teach that class, is that fine, I have my asymptotes, but how do I know where the graph is going in between, right? So that's exactly what our derivative is going to answer for us in this section finally. So how do we find a vertical asymptote? We're going to start with those in a graph. So I'm reminding you of that. A vertical asymptote of a rational function will occur where the denominator of a function is equal to 0 and the numerator is not. So what we're going to do is we're going to try, and of course the problems I'm going to give you are all going to be factorable, so don't worry about that. So we go, again, we're keeping it simple. This is not a calculus class. So you might be like, oh my gosh, this was simple. Yes, it is. So we're going to factor the top. We're going to factor the bottom. First, I'll apply to A. 4 and 2, a plus 2 and a minus, plus or minus 2. There you go. So I'm factoring that quadratic. I'm factoring that quadratic. So as you look at this function right here, it says a vertical asymptote will occur, in other words, it's going to be a vertical line, at all the x values where the function, where the denominator of the function is equal to 0 and the numerator is not. So we're going to see an example by the end, the last one we're going to do, where sometimes when you factor these, just as it happened in 1.1, if you remember, and I know we even did in class, well, in our Zoom session, a problem where one of the factors was reducing and leaving us with a hole. That's what that was all about. So anyhow, sometimes these factors could be reducing, yes? So what we're saying is once you reduced it, it's not a factor of top and bottom, just the bottom, yes? You're going to get a vertical asymptote at each of the factors of the denominator, so or the solutions for the factors of the denominator. So in other words, for this problem here, what would be the vertical asymptotes for this problem? I'm going to continue it down below. So for the function up above, we have vertical asymptotes, and we do not want to write too much, at 2 and at -4, yes? So it occurs where the denominator is equal to 0. So this is equal to 0 when x is 2 and when x is -4. Except for this would be, I'd say completely incorrect, but it's not going to make me happy. What did I purposely do wrong? 2 is not a vertical line, yes? So a vertical asymptote is a vertical line. Look at it. It even says right here, a vertical asymptote is a vertical line, and these are the equations of vertical lines, yes? These are equations of horizontal lines. So when you write an asymptote, you better write its equation. 2 is a number and not an equation. So you need to write that x equals to 2 is a vertical line. The other vertical line occurs at x equals to -4. So these are the equations of the two vertical asymptotes, okay? All right, so it says a hole occurs in the graph, exactly as I said, if you should have a factor that reduces, okay? All right, so not for this one, not specifically for this problem, right? Okay, now how do you find a horizontal asymptote? Let me keep the function up here. How do you find a horizontal asymptote? By the way, even a parent function, where is the denominator 0? At 0, right? So the y equals to, or x equals to 0 is a vertical asymptote. Okay. A horizontal asymptote, it's actually super easy to find. You're looking at the degree of the top versus the degree of the bottom. So if it says the degree of the bottom is more than the degree of the top, of course it says, oops, sorry. So if the degree of the bottom, well, obviously the denominator, is more than the degree of the numerator. So in other words, you have what's called a proper fraction. So there it is right here. So if you have, right, the top is less than the bottom, this is going to go to 0, right? So it's the top is less than the bottom, it's going to be a number less than 1, right? So it's going to, the larger and larger the y values are, the x values are, by the way, the more the fraction's going to get close to 0. So then this is the asymptote you get. So here it is, the degree of the top is less than the degree of the bottom, or as it's written here, the bottom's more than the top. That means y equals to 0 is a horizontal asymptote. I'm going to jump here. If the degrees are the same, as in this situation here, if the degrees are the same, then the horizontal asymptote is the ratio of the leading coefficients. So for our problem up above, from above, because the degrees are the same, yes, you have a 3x squared and an x squared, then you get a what? Y equals 2. Look at the leading coefficient is the coefficient of the highest degree, divided by the leading coefficient, the coefficient of the highest degree. In other words, y equals to 3 is going to be a horizontal asymptote. And again, that's simply because the asymptote, the horizontal asymptote, is the quotient of the division. So how many times does x squared blah 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 go into 3x squared blah blah blah? 3 times, yes? How many times does x squared go into an x, right? If you don't have an x squared there, but a lesser degree, that's 0 times, yes? Now, if the degree of the denominator is less than the degree of the numerator, so in other words, the top is more, higher degree, then you do not have a horizontal asymptote. In fact, you can get what we call an oblique asymptote, which we're not going to worry about. But I'm reminding you because I know you've done that. So you will in fact get an oblique asymptote. Not if it's just, if the degree is the denominator is just less, but it's 1 less than the degree of. So in other words, if the degree of the top is exactly 1 more than the degree of the bottom, that's when you get your oblique asymptote. In other words, the quotient would be a linear factor. Okay, don't want to teach you college algebra again. Just want to remind you of the key parts that we're going to be using in this really short section. Okay, don't worry about this. It's just there because the whole thing was there, so I put it together. We are now going to write functions from the graph. So we're just going to have the graph and draw the and go and use it to draw the function, but not backwards as you have had to do in college algebra. Okay, so I'm going to show you the steps. Pretty much we're going to have to go through this. Many of them, again, as I said, do repeat from college algebra. So we're going to do a few problems. Our goal again is to do what? Graph the function, yes? By doing what? We're adding on something you didn't have in college algebra, and that's the what? Sine diagram for the first derivative. Information about the first derivative. So we will further on add the first derivative to help us more. What I've just talked about is just review, okay, from college algebra. So the other thing again, when you will read the textbook, you will kind of see both methods. So I wrote in the beginning of all those examples in the book, hey, from college algebra, we know, look at the degrees, so on and so on. So the review of what we just talked about. Professor Kemp wanted to go the calculus way, and he's actually really going through the problem as if you didn't have this information from college algebra. So he's really showing you, or wanted to put in the proper calculus way of finding the vertical and the horizontal asymptotes by finding infinite limits and so on and so on. You don't have to do that. If you'd like to read to see, again, if you were in a calculus class, yes, that's what you'd have to do. But my theory is you've had to get through college algebra to get here. You were forced to have that course as a prerequisite. So you might as well use that prerequisite, put it to good use, right? You bring already some knowledge. We're not in a calculus class. Let's use what you've already learned, okay? All right, so here it is. As I said, there's going to be a few steps. So when you solve these problems, again, try and, I'm just making it simple for you guys. That's all I'm saying. Okay, so it says, we're not just going to jump straight into the derivative. That's not going to help much. These graphs here have funny business, as I said. What do they have? Vertical, horizontal asymptotes, maybe holes, possibly holes. So we need to put all this stuff to good use. So this is what I'm going to do. The first things first, if your function is not reduced, if your polynomials at the top and the bottom are not factored, that's the first thing you should be doing, right? Otherwise, let's jump into finding vertical and horizontal asymptotes. Okay, so it's all factored out, all reduced out. What is the value that makes the denominator equal to 0, right? That would be a 5. Yes, by the way, this is the domain of this function. Yes, in other words, it's all real numbers, but not 5. I don't want a 5 in this function, right? That makes the bottom 0. So I'm going to have to skip over it. So exactly as we talked about, anywhere where the denominator is equal to 0, that's where you get yourself a vertical asymptote. Okay. Horizontal asymptote, it said, look at the degrees of denominator versus numerator. So it said, if the denominator is more than the numerator, I kind of would like to see it backwards. I guess you start with the top. So if the top's degree is less than the bottom, then automatically y equals to 0 is a horizontal asymptote. Okay? Degree of denominator more than the degree of the numerator. And again, what's the degree? Is the highest power, right? So the degree of the denominator is 1 because you have an x to the power of 1. The degree of the numerator is 0, right? You have no x term here. So this constant term there is an x to the 0, if anything, right? X to the 0 equals to 1. Okay, so vertical, horizontal asymptote. Before, again, okay, maybe we'll do that next at the end. Remember how I said it's really helpful? Yeah, I'll do that here. I'm just decided. It's really helpful to plot in a few more points if we can. And what are the few points that we can plot in? Are the intercepts, yes? So in a college algebra class, that's what you did. You found the asymptotes, you found the intercepts, and then you tried to weave the graph through. Okay. So what are the intercepts? Make x equal to 0, find the y. Make y equal to 0, find the x, right? So if I make x equal to 0, by the way, yes, I'm going to get that y is equal to negative 2 divided by negative 5. Well, that's a positive 2/5, yes? To make y equal to 0, that means your fraction is going to equal to 0. As I keep saying, a fraction only can equal to 0 if the top is 0. You could make or you could think about multiplying both sides by an x minus 5, and you get the negative 2 equals to 0. That's not possible, right? So in other words, that's not going to happen. Plus, already as we said, the y equals to 0 is a horizontal asymptote, so the graph is just going to get close to it, but it's in fact not going to touch it. However, this is a good point to hold on to, okay? All right, so now comes the calculus part, the part that's going to help us further, which is what? Find the first derivative and make a Sine diagram for it. Okay, so this is just the review part. Next time we can go through a little bit faster. All right, so here's the derivative. Now, the point is, these are not so easy. Why? Because they're quotients, so we have to use the quotient rule. So the quotient rule says, take the derivative of the top, but the derivative of the top is the top is a constant, so its derivative is equal to 0, times the bottom, minus, take the derivative of the bottom, by the way, is a 1, times the top, which is a -2, all over the bottom squared. Okay, so when I simplify this, that's a 0. -1 times -2 is a +2 over x minus 5 squared. Okay, so what do I want to do? I want to find the critical numbers. What are the critical numbers? The critical numbers are where the derivative is equal to 0, but same thing. Can this fraction equal to 0? No, the fraction will never equal to 0. Why? One more time, I'll put it up here. Because the top can never equal to 0. The top is a 2, and 2 is 2, and that's the end of the story, yes? Okay, if it can be 0, could it be undefined? That's another place where I can find critical numbers. Yes. When does this fraction become undefined? If the bottom is 0, right? And the bottom is definitely 0 if x is equal to 5. So this is our critical number. All right, let's move on and make this sine diagram. So how do we make a sine diagram one more time? We are going to put the x's, the derivative, and then the function right down at the bottom. Where's my green? There it is. Okay, so the only critical number we found between -infinity and +infinity is 5. Okay. All right. What happens with the derivative at 5? It's undefined, yes? Then it's a sine diagram. So I'm looking at the sine of the derivative, yes? Is it positive? Is it negative? Just as in the last section. So you're welcome to plug in any value you want. Put in a 0, right? Pick a test point between -infinity and 5. And plug it into your first derivative. That's whose sine we're looking for. But the thing is, you're plugging in a 0 here. You get a -5 squared as a positive. 2 divided by 25, that's a positive, yes? Put in a different value, more than 5. Let's say 6. 6 minus 5 is a 1. Square that is a 1. 2 divided by 1, that's a positive as well, okay? So by the way, look at that. The top is positive, the bottom's being squared. And anytime you square a number, it's only going to be positive, yes? So for sure, you didn't even have to plug in any points. You know that this is going to both, it's always positive, by the way. Okay. So what happens to my graph? It has to go up, and then it has to go, is it going to even out here? No. There's a break. And by the way, there's a break in the function itself. There's a vertical asymptote there. So this is the key fact. And let me show you what and why this is so awesome. This is what I know. I know that x equals to 5. At x equals to 5, I have a vertical asymptote, yes? Right here. I know that y equals to 0 is a horizontal asymptote. So the graph is going to go just the same as the what? Just the same as the 1 over x function. Is going to have some breaks. It's going to have a vertical break. It's going to have a horizontal break. Here, I'll make them in blue if you want. It's going to have a vertical break. It's going to have a horizontal break, yes? The other thing is what? Now I know the graph is going to go somehow here, yes? either down below or up above, down below or up above. But this one's telling me right away where. I know the function's increasing. What does it mean it's increasing? It means it's going to go up. And if it's going to go up, it has to come, again, the graph has to come from down here or down here, yes? So it's either above or below. But the thing is, because I know the graph is increasing, I know it goes above. Also, the other thing I know is this y-intercept. So it's going, 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 going. Crossing at 2/5, by the way, yes. And then up along the vertical asymptote, yes. So that's what the asymptotes are. They're going to get closer. It looks just like the 1 over x, right? And then I have to jump over on this side, and what's going to happen over on this side? Is the graph up here? No, because up here means it's going to go down, yes? So it has to go up again. And as you see, there are no other crossing points, right? The only crossing point through the axis was 0, 2/5, which we considered. The rest of it is just there. Okay, all right. So let's take a break on this video, and we're going to do 2 more examples in the last video.